Okay, so let's continue with things we were doing, the Jacobian over Riemann surface. Over the Jacobian map. And Ovel's theorem. So there are three topics here. Okay. Instead of recalling what we did just right now, let me start with something new that we need. That is intersection pairing. Intersection pairing on H1 of X and Z. So remember that H1 was a singular homology of X within integer coefficients. So this is singular homology of X with integer coefficients. Yeah. And you can take singular homology with coefficients in any abelian group for that matter. So that's but Z is kind of more or less most important case. I mean, for elementary stuff at least. So what is X? X is a compact Riemann surface of genus G. So actually, what the stuff that I'm going to do now, it's independent of Riemann surface structure. It's purely topological thing. So, in fact, it is enough for what I'm going to do now to have X a smooth, in fact, even topological smooth, which is the same as topological in 2 dimensions, even topological closed oriented surface. That's it. Just a topological object, closed oriented surface. For now, it's enough to have just that those properties. That's enough. I won't use complex structure on the Riemann surface for now. Okay. So this I will recall that this H1 of X and Z was the quotient space was closed one cycles, right? Closed singular in one chains divided by exact singular one chains. So it's a quotient space that we define. Now, what we want to do, so intersection pairing is the following thing. Pairing. So it's a map, it's a bilinear pairing, H1 of X and Z plus H1 of X and Z. Did I say oriented here? Well, oh yeah, okay, I said it's quite important. H1 of, but Riemann surface has a canonical orientation, as we know, right? So it's just all conditions are satisfied for a compact Riemann surface here. So h1 of x and z to h1 of x and z to z. So it's a non-degenerate. So I haven't defined it yet, but after I define it, it turns out it is a non-degenerate skew symmetric or alternating pairing. So how we define it? I mean, there are different ways to define this, but the classical original way is reflected in the name of the object. It's called intersection pairing. So what we're going to do, we will intersect curves here and curves over there and count number of intersection points up to multiplicity. So basically, what we're saying is that if you have a chain, closed chain, representing class times C1 times C2, closed chain that represents a homology class here, another closed chain, another homology class here. So this is by definition number of intersection points, or I say intersections of C1 and C2, counting with multiplicities. I can tell you. I mean, multiplicity is not that important. What is important is counting up to orientation. So let me put it this way, counting up to orientation. Okay, I will explain what I mean. Okay. So what do I mean by this? Let me explain. So what we do is the following. Okay, so maybe I'll just erase this one. So you just take maybe a cycle, which is okay. So maybe I just draw. No, that's okay. So you have this cycle or chain, closed chain C1. So for example, you have a closed smooth curve which has some orientation. It goes in this direction. So this is C1, and you have another chain C2, right? So for now, it's just like that. And then this has this orientation. So if you look at these two things, you notice that there is an intersection point here, and there is an intersection point here. Now, so what is that should be C2. Oh, this was the arrow, yeah. Okay, when you look at this point, we make sure that they intersect in a transversal way. So intersect transversally. Okay, so what does it mean? It means that they don't intersect like this. This is not transversal intersection. This is a bad intersection. I will tell you how to get rid of this situation like that. But imagine they are just transversally intersecting. Now, then you look at what happens at this point. So we want to do C1, C2, right?
Is that intersection a segment rather than a point?
What's that?
The non-transverse intersection.
Yeah.
Is that?
Well, it means that the tangent spaces coincide at that point for the two curves.
So they intersect at a single point.
They intersect that?
At one single point.
At one single point, yeah. Yeah. So yeah, the chalk is not that fine to. Yeah. Okay. So, but basically, what it means that the tangent spaces of the two curves at that point, they are along the same line. So you cannot define a two-dimensional space as I need it now. You will see why I need this. Okay, so now we want to define C1 dot C2. So what we do, we just look at C1, which is this one. You draw tangent space here, and this is C2. So, okay, so there is this tangent vector E1 and this tangent vector E2. And then what you do, you notice that orientation defined by E1, E2, is it the same orientation that the space has at that point or the opposite orientation? Because it's going to be two-dimensional anyhow. So either the same orientation or the opposite. So that's equal to +1 if E1 and E2. So let me put it like this. The ordered pair actually, E1 and E2, has the same orientation.
Oh, sorry, what? E1?
Sorry.
What is E1?
E1 and E2 are tangent vectors to the two curves at that point. Yeah. So if E1, E2 has the same orientation, as the surface orientation at that point. At P. So this is the point P, right? Now, let's see what happens at this point. Now, if you look at this point, so this is P1. Let's look at point P2, right? So okay, so if you look at point P2, here is E1 now, again, so let's call it F1 maybe. And for E2, so this is going in this direction. Yeah, okay, so I've got here, so let me make sure I understand. So E1 and E2, yeah, this is standard orientation. So this is F1 and F2.
Is F1 opposite?
What's that?
Is F1 the opposite direction?
F1. Oh, yeah. Thank you. Yeah, exactly. That's why I was worried about this a little bit. Yeah. So this is this direction, yes. F1 and F2. Exactly. Now, in this picture, so this is P2. You think F1 and F2 has the same orientation as the orientation of the tangent space at that point?
Is that the opposite orientation?
It has the opposite orientation. Yeah. You see, if you look at F1, F2, if you want to move F1 to F2, you have to go counterclockwise. But so you have to go clockwise. But the orientation of a space, I'm using orientation of the surface or plane in this case to be just clockwise, counterclockwise. So they have different orientations. So what I'm saying is that in this case, in this example, it looks like that C1 times C2 is equal to, okay, so there is this point +1, minus 1 is equal to 0. Okay, so this is 0. Now, here is the problem. There are a lot of issues with this definition because, so I'm just choosing two cycles. I mean, they may be far apart from each other, and they may intersect in a non-transversal way. Maybe they intersect like this. How can I do this? So the theory that was originally developed actually makes sure that you can always perturb these chains within the same homology class so that the intersection was actually always transversal. And they intersect in a non-degenerate way. So this can be done.
Is
And it's,
this well?
yeah, that's a good, and it is well defined, yeah. And it is well defined. So if you want to choose this geometric definition, which is really good because you just see what's going on. The challenge is to show that this is well defined. but it turns out to be well-defined and is nice thing. And you check that it is non-degenerate and also alternating. So if you change, if you do C2, C1, in this case, of course, it's 0. But if you do C2, C1, you get a negative one because of orientations at intersection points reverses. So this is the classical definition. But then there is a formula actually you can use. So let me give you the more modern definition that you learn maybe in algebraic topology, which is, I will tell you what it is. Okay. Okay. And then I will look at examples that we need. Okay. Right. So more modern definition. There is something called cup product. Yeah. I'm a bit hesitant using that because homology doesn't have a product in that sense. So, okay, let me not give you more modern definition. Okay, I may. So let me just use your intuition and then so let's look at an example. Okay, so the example that we want is x equal to this one, right? Okay, so we have a surface of genus G, and I want to look, of course, I mean, again, these calculations, which I won't do it because this is part of algebraic topology, is another course, but this is H1 of X and Z. I told you what it is. Do you remember what I told you? What it is, the result of this? This group has been calculated, can be calculated using standard tools of algebraic topology. I told you what it is.
A1, B1, which is B0, and then other by counters.
You're thinking about homotopy, and this is homology, which is easier actually.
So Z to 2G?
Huh?
Z to the
Z to the power 2G, yeah. I show that this is Z. Oh, you're right, actually. You just, I don't know what did you say exactly, but you're possibly, okay, so let me not comment. Okay, I'll get to your answer. Z to the power 2G. With generators, now let me tell you, with generators.
Actually, one here is substrate.
Huh?
H1 should be down here.
Oh, it should be down. Yeah, very good. I'm glad that, Gabi, you pay attention. Now you're a topologist. That's good. Half of the job is to worry about down or up indices. Mathematics, just okay. It's part of the, practicing, respecting the language. With generators, A1, B1, A2, B2, AG, BG, right? With these generators, which geometrically I can write what these generators are. I can show you what these generators are. Here is A1, for example. It goes around this one time. This is maybe, so this is A1. And this one goes around the same hole, but in this direction. This is B1, right? Okay, then for this one also, we just pick A2, and this is, okay, so this is A2 now. So, okay, let me put it here, A1. This is A2, and here I just take, I want to go in this direction, and this I want to put B1 here, and A2, and I go this direction, B2, and then this is, say, last one, AG, and then I just go around BG. and I just use this orientation. Okay, so these guys, these generators are the way they prove to you in courses in algebraic topology that these are. But this basis generators, and in fact basis, I should say, because this is a free module of rank 2G, right? It's a free module of rank 2G, and this is really a basis. Although it's not a vector space over a field, it's just a module, more complicated object, but it's still, it has a basis, and it's just this. Now, this basis has a very nice property. This is called a symplectic basis. Symplectic, I should not write with I should write with Y. Symplectic basis, i.e., so it satisfies these conditions, which are the following conditions. We have got first of all, AI dot AJ is equal to 0 if I is different from J. BI dot BJ is equal to 0 again if I is different from J. And AI dot BI is equal to 1 for I less than G bigger than or equal to 1. It has these properties. Okay. So if you wanna check this, you can see by the geometric definition I gave you, it's clear that this satisfies these properties. Because if you want to take the intersection pairing of this cycle with this other cycle, well, I'm using orientation of the surface, which is just as embedded in the tree space, and just I would say counterclockwise orientation is the positive orientation on the surface. So this is A1B1. So this A1B1 is the same orientation as the orientation of the surface at that point. So this is has only. So you see, the point is that these two curves now has only one intersection points. These two generators, A1, B1. There's only one intersection point, and it's positive at that point. If I chose B1 dot B2, it would be -1, would go the other direction. Okay, so same thing with others. Why didn't I write this? Okay, so I should have done this here as well.
What about AI.bj?
Huh?
What about AI.bj?
AI dot
BJ.
BJ. Oh, yeah, they don't intersect.
If it doesn't intersect, it's 0.
It's 0.
What if they're the same one?
Huh?
AI dot AI.
AI dot AI is 0. Why is it? You say, yeah, you say why it is 0.
Yeah.
That's a good question. Yes. So yeah, you say, okay, so I want to do so here is AI dot AI. You see, what I said is that you can always change it a little bit, put it in general position. So you can, within the same homology class, you can perturb this a little bit so that they become non-intersecting.
And it's the same situation as that one.
Yeah.
Okay.
It's always like that. So this is, I believe, Lefschetz was the first one in defining. Maybe in 19th century there was also some ideas, but Lefschetz was the master of this sort of conception. So, I mean, this works. I mean, and these are this basis, and this is the basis that we need in order to work on. Okay. Any questions about this? Okay, so this is the intersection pairing, and this is the symplectic basis in that space that we need. Another gadget we need is Poincare duality. So let me write it down a little bit. By the way, this works in much more generality. You can have maybe higher dimensional spaces, but yeah, at least this can be generalized to much more higher dimensional spaces, basically. Intersection pairing, for example, I mean, in general. So if you have a topological manifold X dimension n closed, say smooth, even I believe topological is enough, then you can define something like Hi of X plus Hj of X to Z. I mean, X and Z I put here. X and Z. If as soon as I plus J is equal to N.
Sorry, if I have A dot B, then I have B dot A, are they?
Minus is equal to minus B dot A. Because orientation changes at the intersection point. If you traverse one on the other, yeah.
So in such an X, can you also take H0 cross H2?
H0 cross H2, yeah, that exists also.
Oh.
All these things exist, yeah, for general n-dimensional manifolds. So. But we don't need it
Because
now.
all of our manifolds are two-dimensional.
What's that?
All of our surfaces are two-dimensional.
Oh, I hope so.
So
That's
we
all
only,
this.
so we're only concerned with H1 cross H1 and H0 cross H0.
Actually, H1 cross H1, yeah. That's what it is. Any other questions? Okay, so let me now continue. We need a little more of Poincare duality. So again, this is a very special case, but that's what we need. This is just for surfaces. Okay, so X again is a smooth, closed, oriented surface. So you remember we defined the Rom groups of this H1, the Rom of X. You remember what we did? We defined it to be a space of closed, smooth one forms divided by divided by exact one forms. Okay, so just be careful. I'm using also the Rom with complex coefficients, which is an easy modification of the original definition. That's not a problem. And these are closed one forms. This is the omega equal to 0. This is the closeness condition. And exact, you remember omega was equal to d of f, differential function. This is exact expansion. So basically, we are taking these are topologically trivial exact ones. So we just mod them out. The rest is the quotient is interesting object is a topological object. And again, for actually in this case, computation shows H1 the Rom of X. It's isomorphic to okay, so because I'm working with complex coefficients, in this case is C to the power 2g, R to the power 2g with real coefficient. If you work with real coefficient, which is usually at first when you are introduced, people take wrong thing with real coefficients, but we can just, I need it now for complex coefficients, so that's okay. All right, now what? Now what we want to do? Okay, now this Poincare pairing is the following. So there's this pairing H1 of X and Z. I mean,
Wouldn't
actually,
it be R4G?
sorry.
If it's C2G, wouldn't it be R4G?
Oh, no. I mean, no, when you complexify this vector space, what do you get?
CG to the G.
Huh?
CG.
No, I mean, so yeah, that's a good point. So, but I mean, R to G, right?
No.
This is a complex, this is a real vector space.
Yes.
If you complexify this, means that I take C, tensor this guy. What kind of vector space is that? Can you tell me what vector space is this?
CG.
It's not CG, it's C to the power 2G. Why you're saying CG?
So we consider R as a C module.
Hmm?
We consider R as a C.
Yeah, exactly. No, not as a C module. If you consider R is not a C module, I'm thinking of this as a real vector space, and this also as a real vector space. I just
But
tensor.
what are you tensoring over? Tensoring over R?
Oh, yeah, tensor over R, yeah. Do you see that? Yeah. You see that? It's okay not to sing it. I mean, so yeah. Yeah, so anyhow, so this is we are taking complex. It was a good. It was good to pay attention to this. Yeah, good, very good. Okay, so now I want to define this thing. Actually, I want to define this with even complex coefficients. So this is singular homology with complex coefficients cross Duram. Again with complex coefficients. I want to be over complex numbers, as you can see, we are over Riemann surfaces to see. So how is it defined? This is essentially integration of a 1/4 over one cycle. That's just integration. Yeah, okay, so this is integration. So what does it mean? It means that, so basically what it means that we have got, it means that we have got now, so if you have a cycle here, and a 1/4 class of a 1/4, okay, so comma, it's mapped to integral of omega over c. I mean, at first you define this for usual chains, and then what is this guy? It consists of chains with complex coefficients. You linearly extend, C linearly extended to all chains with complex coefficients. And this map is well defined. So Poincare duality in this case says that this map is actually non-degenerate and is a perfect duality. So your perfect duality now comes into the picture. So Poincare duality says a perfect duality means that it's non-degenerate pairing. Poincare duality says that this pairing is non-degenerate. Okay. Okay. Now, what you need then is, it means that basically, if you want, for example, this Duram cohomology is isomorphic to dual of this singular homology, which actually turns out to be singular cohomology. So isomorphic and vice versa. So this is like the duality pairing. Now, what else I need? So now let's go back to symplectic basis. Choose a symplectic basis. A1, A2, AG, B1, B2, BG for H1 of X and Z, which is isomorphic to Z to G. Now what we do, we just choose Poincare duals of these things. Let omega 1, omega 2, omega G, and eta 1, eta 2, eta G be Poincare duals. Poincare duals of the symplectic basis. A1, A2, AG, E1, EG. So you can actually understand, because this looks very abstract, but you can intuitively understand Poincare dual. That's not a difficult thing to understand. So let me write the conditions so they satisfy. The following conditions: integral of omega I over AI is equal to 1, and integral of omega I over AJ is equal to 0, and integral of omega I over BJ, they're all but BJ is equal to 0, yeah.
What
Yes.
about omega I over
Wait,
bi?
let me just think. It says omega AJ. I mean, this is for all. This is for all J different from. So here is J different from I, but this is for all J, right? Yeah. Yes. Question?
Oh, I was wondering what happens when omega I and bi are the same, but it's 0.
Yeah, it's 0.
Okay.
Yeah. I mean, in that book I mentioned in my last message, in Fulton's book, for example, you can read that there's a section which describes this, and also in button 2 you can read a very, very clear presentation of Poincare dual, how to construct Poincare dual of cycles. I highly recommend those. Actually, button 2. You should learn topology from that book first, rather than reading. I don't know, Hatcher and these things. It's just a bad book anyhow. I'm on record saying that. I stand by my reason. You don't learn topology by reading Hatcher.
I don't think anyone in this room will disagree with you.
What's that?
I said, I don't think anyone in this room will disagree.
Oh, I'm glad. Because I mean, it's just such. I don't even know what to say. But you open button 2. I mean, it's a work of a master. Expositor, master mathematician, and 2 just took notes. He was Bot's student, and the notes, I mean, turned into a beautiful, wonderful, amazing book. Oh, you can even fall in love with that book. All right, so okay, so I'm just using this now. So to have this in mind, so now the next thing is I need a pairing in another pairing. Yeah, I need the analog of this pairing for yeah, so basically so this is kind of what's it called? Yeah, intersection pairing. This is the analog of actually intersection pairing. This time on H1, the RAM of X. Again, mind you, it could be complex coefficients, which is okay. So then basically what it is the following. So you just have a class omega and another one for eta you send it to integral of omega with eta over x. Okay, so let's see. Omega is the one form, it's a closed one form because it's a class, right? So this is a closed one form. Same with this, right? So this is a two form, and you can integrate two form over two-dimensional manifold oriented. Always, it is compact, so there's no issues with convergence. Okay, so this is a two form, and you integrate. Now this, so this is nice. Now, okay, so this is really a symplectic two form. I mean, it's first. I mean, here it's very easy to see that it's antisymmetric because if you switch the order, you're gonna get, you see, omega wedge eta is equal to minus eta wedge omega, right? So if you switch the order, the sign gets changed. So working with one forms, things are much easier actually to see rather than with singular homology, which was needed some intuition to, you know. So basically, that technique I use is called putting things in general position. I mean, there was always this classic argument of like when you prove Bezout's theorem, the curves has to be in general position. Otherwise, you have again this issue of two cycles or two curves completely coinciding with each other. But you can just perturb it a little bit. If they don't intersect, then that's fine. Okay, so this is this one. Okay, so I need last piece of I promise this is the last piece of things from topology that I need, and it's a bit actually involved. Not to write it down, but maybe grasping it. It's a bit involved. That's actually yeah. So that's just a little bit of Hodge theory I have to use. A little bit of Hodge theory, just a little bit. It won't be too painful. A little. Oh, it's okay. Actually, it's a beautiful theory. A little bit of Hodge theory. So actually, I can give a general introduction for those of you who haven't seen this because it's a beautiful theory. So remember, I mean, so now we need a Riemannian metric. So I'm going actually to work in general for n dimensions. So let X be a closed, oriented Riemannian manifold as a Riemannian manifold. So yeah, closed, oriented, smooth, of course, Riemannian. When I say Riemannian means that it's a smooth because I could not define Riemannian metric otherwise, right? So okay, so the Ram theory, you remember H K, the Ram of X again was closed. Again, I just write the formula again, closed K forms divided by exact K forms. So these are the space of all closed K forms divided by space of all exact K forms, and this is. So in this definition, we didn't use Riemannian structure, right? Now, if you use Riemannian structure, you can actually write this in a much better form. In other words, you can define something called harmonic forms, and then turns out that the space of harmonic K forms is actually isomorphic on the nose to the Ram cohomology. So let me define using the Riemannian metric. G, you define another differential, second differential. So this differential is called D star, which is really is really inner product adjoint, Hilbert space adjoint, but that's okay. d star from omega k, from k forms of x to k minus 1 forms of x. I mean, this is for all k, right? Remember, d was from omega k of x, remember, to omega k plus 1 of x, right? This was d. D always increases, the theorem always increases the dimension, right? You always increase by 1. But this strange differential d star, which is really adjoint of this, because using Riemannian metric, you can put inner product structures here, and this turns out to be the adjoint of it. It's not obvious that it exists because this operator is not a bounded operator, and this is not a Hilbert space, so you have to work a little bit. And there is an explicit formula for this star, it doesn't matter. Okay, but this is, so then you define something called Laplacian, which is called Laplace-Beltrami operator, actually, so let me write it. So this is, I mean, using d and d star, you get delta, which is equal to d plus d star squared, which is d star plus d star d. Now this this delta is called Laplace-Beltrami operator because it's a generalization of Laplacian really on flat space. It's just a Riemannian generalization. Is Laplace-Beltrami operator. Actually, I believe on the level of forms, the first person who looked at it most probably was Hodge, William Hodge. So maybe, so I should call it maybe Hodge in 1940s. Well, in mathematics, it's always very dangerous to say who started the things because it's always very dangerous to say this concept was initiated by this person. So almost always wrong. There is, you can find always remnants of this concept in older literature and older things. So, okay, but the person who put it in really great use was William Hodge in 1940s. So this delta then, remember, goes from omega k of x to omega k of x for all k. Remember, this goes one dimension up, and then I use one dimension down, it goes back, and then the other one goes this direction. So they conspire together to define this thing which doesn't change the dimension. So now we define harmonic K forms to be just kernel of Laplacian, just as a harmonic ones, kernel of delta. Then this Hodge theorem, the main result of Hodge theory is for Riemannian manifolds. I mean, for complex manifolds, you take this result and then you use extra symmetry for complex structure. You develop, you prove much more results. But but you need this result to start with. The Hodge theorem is the following: that the map from arm k of x to hk Durham of x is a bijection. So this basically means that for any cohomology class, there exists a unique harmonic form that represents that class. See, I mean, that's okay. So, I mean, in the case of Riemann surfaces, this actually goes back to Riemann. Riemann proved this using his methods. Okay. So now, okay. So maybe I should stop and see if you have questions.
Does this have anything to do with harmonic function?
Yes, if k is equal to 0, this goes from smooth functions to smooth functions. And then the kernel of Laplacian is exactly a space of harmonic functions. Yeah.
But doesn't the other one has to go down once and then up?
Oh, that's 0. So yeah, for yeah, okay, so good. So for harmonic function, this is d star d. I mean, dt star is 0, right? Okay, so just say, but this is equal to 0.
Oh, so the negative, sorry, the C.
Yeah, we always put in when you compute cohomology, right? If you have a chain complex of the manifold, it exists between dimensions 0 to n. Above n, you put 0, and below n also you put 0, and then you get a complex which is defined, indexed by the all integers, and that's convenient.
Okay.
Yeah, this is a good question. So this is really, yeah, this is harmonic functions, but this is for forms now, all forms, I mean, fine. So, yeah, I mean, that's, okay, I mean, yeah, I mean, but as I said, I need it only for k equal to 1 and x two-dimensional Riemannian manifold, right? So that's, okay, so there is now, so now in the case of, so now remember, so now let X be a Riemann surface, so compact Riemann surface. Then basically what happens is that so H1 Durand with complex coefficients of X is isomorphic to omega of X, direct sum omega bar of X. Okay, I gave you a quick introduction to Hodge theory for Riemannian manifolds. But here there's a little bit of subtlety still. I mean, because if you have a Riemann surface, there is no Riemannian metric there on the Riemann surface, right? There's no metric. I mean, it's just it's a complex structure. So you can argue like this to bring. So you can say by the general result for conformal structure, I told you that there exists a unique up to conformal equivalence class of Riemannian metrics that gives you that complex structure. So you have to be careful about that. Or we can avoid using Hodge theory and then just citing this result. So let me tell you what this. Okay, so there's a little bit of confusion here in this. So what is omega of x? Remember, omega of x was a space of holomorphic one forms. I mean, of course, complex valued, always. I mean, I don't even have to say that because it's holomorphic. Space of holomorphic one forms. And omega bar of x, this is a space of anti-holomorphic one forms. Anti-holomorphic. One forms. So what we mean by anti-holomorphic, so i.e. locally, any omega which is in this one can be written as f of z dz bar. We can write it like that. Now, this omega of x is actually, if you follow these definitions, turns out to be more than just a closed one form. It's really, these are really harmonic, and this really corresponds to harm one complex value of x. So these are all harmonic one forms which appear in this form. But again, I have that ambiguity now for the use of Riemannian metrics, which I have to yeah, it can be avoided, but yeah, it takes some more more definitions. So there's some more work. Okay, so now we need two things, simple observations. Any questions? Okay, we need two simple observations. Okay, maybe I erase everything here. So recall that we have this thing from H1 around intersection pairing X cross H1 around X with complex coefficients as always to C. So alpha and beta goes to integral alpha with beta. So lemma is the following. There's an interesting lemma here. One is that if omega is yeah. So first of all, I mean, you say okay. I think I want to denote this actually by alpha and beta. So this is a different notation now. This is a pair that's mapped into this number, but it's a notation for that actually pairing. So sorry about that. Yeah. So first of all, if alpha and beta both belong to omega of x, then integral of alpha which, do I use alpha? Yeah, alpha which beta is equal to 0. So the way that these guys, the polymorphic bond forms sit inside this cohomology is kind of special. It's they're 0. This inner product is 0. And second one is that I believe for any alpha non-zero. So yeah, okay. So I need a condition. If alpha is a non-zero holomorphic one form, non-zero, that's my condition. Then integral of, I believe integral of alpha wedge alpha bar, which is the inner product. So yeah, so integral of alpha bar, which is equal to that, it's strictly positive. Yeah. Yes. So we need these two conditions, two properties for this. So proof. Case one. Let's see how we can prove that. Well, alpha is a holomorphic bond form, right? So locally we can write it as f of z dz, right? Locally, alpha is equal to f of z dz, right? Okay, so this is f of z dz. So if you take and beta, if g of z is z, where f and g are local holomorphic one form functions, locally holomorphic function, and this is. So from here you conclude that alpha which beta, right, is equal to f of z, g of z, dz base dz, which is of course 0. Dz base dz is 0. And one form wedge product with itself is 0. So one is done, easy. Two, now let's look at this one. So if alpha, again, is f of z is z, so we can write this as equal to f of z dx plus I dy, right? Locally we can always do that. And if you look at what is alpha bar, this is f of z bar, is z bar. So this is equal to f of z bar dx minus I dy. I'll finish soon actually, so. Okay, so now. Okay, so from here, you conclude that alpha, okay, so let me put it like this, I, alpha, alpha bar. Okay, so now, no, I mean, so let me compute I, f of z, dz, veg, f of z bar, dz bar. So this is equal to I times absolute value of f of z squared. Now you have got dx plus I dy times dx minus I dy. What do you get? Dx veg dx is 0. Dy veg dy is 0. You get minus I dx veg dy. And then I've got I dy veg dx, right? Okay. So if you multiply, of course, this is nothing but minus I again dx veg dy, right? Okay, so if you calculate that, that comes out to be equal to absolute value of f of z squared. And then you have got in that local coordinate dx veg dy. Because I2 is -1 and minus is +1. So that I disappears, then this is like dx veg dy twice, actually. Okay, so on each coordinate patch, this is this quantity. Okay, we know that alpha is non-zero, so there is at least one coordinate patch. Well, this quantity is non-negative because this is non-zero at that point. Okay, so then the integral and at other points is bigger than or equal to 0 because you see when you integrate, you define. I mean, you can imagine you just chop the space into small coordinate patch and you integrate on each of them, and this just works. Anyhow, so. It implies that I alpha bar is positive. So you can then, we can use these two things to prove what is called Riemann bilinear relations, which will be the last thing I will do. I won't prove it, but it follows, okay, from this. So we need everything now. Using these last two results, plus existence of a symplectic basis. Symplectic basis. I mean, choosing a symplectic basis actually for H1 of X, Z, and its Poincare dual. You can, it's a straightforward algebraic calculation. Let me write the result. We get this Riemann bilinear. So this is a theorem which is called Riemann bilinear relations. Absolutely fundamental. Which is, says the following. For any two holomorphic one forms, alpha and beta, sum j from 1 to g integral alpha over aj. This is part of the symplectic basis times integral beta over bj is equal to sum j from 1 to n integral beta over aj times integral alpha over aj. bj. You see, we keep aj, bj as summing over our indices, but we change the order now, alpha, beta, and then beta, alpha. This is a consequence of property 1, alpha, beta equal to 0. This follows from the fact that if alpha and beta are two holomorphic, sorry.
G at the top.
Oh, G, yes. You have good eyes, Gobi. Very good. Excellent. I'm glad you pay attention. That's great. Yeah, so this is nice. This follows from the first property. In the previous lemon. And there was this strict positivity, and this strict positivity also so this is one actually, and the second one, which is this is strict positivity. If you use it, you get the following relation, which is I sigma j from 1 to g integral alpha over aj times integral alpha bar over bj minus integral alpha bar over aj, changing the order, integral alpha over bj. Yes. This is positive. And this follows, as you can see, its structure is exactly like second part of this previous one. So this follows from part 2 of previous level. And the point of these two these bilinear relations is that it shows that actually this the period lattice is exactly a lattice of rank 2G. So no information is lost when you push it inside omega x door. So now it's time to stop. Is this too much going on? But so we shall use the Riemann bilinear relations to show that. So let me just write it. This actually quite immediately implies that Riemann bilinear relations implies that the period lattice, which was, you remember, it was the image of, which is equal to its image of this map, the period pairing map, which is goes from H1 of xz to omega x star, right? Here in this space. This image is a lattice of rank 2J, 2G. Okay, we know that this is just a lattice of rank 2G. I mean, this guy is a module, this is Z2G, right? And this period pairing here, which images this period lattice, it doesn't kill any elements of homology. It really keeps them separate and has full rank which is this one. This follows immediately from these two relations, but I will, and much more, of course. It shows that the image here is of a very particular shape. And so we come back to this. So we define something called polarized abelian variety. And then I will come back to Abel-Jacobi map as I defined last lecture. And then I will prove Abel's theorem, which is still quite an amazing thing, how Abel could prove this long before Riemann. There was no idea of Riemann surface, there was no geometry. He just did it by manipulations. I mean, amazing. I mean, and his paper, one of his most important papers was lost, actually. He couldn't get a job all his life. He died in depression, poverty, and disease. He didn't get a job. And when he died, actually a job offer came a few days later after he died. He had such a tragic life. And he died at the age of 27. So he was as tragic as Gallo was, I think. But he did much more in a way. I mean, he published a lot of papers because he was just publishing papers when he was very young. So he was publishing papers incessantly. So Gallo did not even, they say even Gallo worked for 1 year, not even 1 year actually, actively, maybe a little less than 1 year, all his life, I mean, just 1 year. I mean, he spent time in jail, you know that, and then he was also, I mean, it's unbelievable. Okay. It just means such a stupid word, right? There's no justice.